Swayam Prabha. Digital India. Educated India.
Welcome to lecture 27 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is non-linear regression models. Now, the linear regression models which we have discussed so far are quite popular because these models are simple to estimate. You can easily study the properties of the estimators of regression parameters, etc. But in many applications, linear models are not appropriate. In fact, in many applications, if linearity is not an appropriate approximation, or you cannot transform the non-linear regression model into the form of a linear regression model by using a simple transformation, then you cannot apply the linear regression model. In such cases, you require some non-linear regression model. Then the problem with non-linear regression models is that how to estimate the parameters of these models, and then how to study the properties of estimators of parameters of these models. So, in this lecture we are going to study different non-linear regression models and then estimation procedures for these non-linear regression models. So, linear econometric models are widely popular in economics and other applications. Because of their simplicity in estimating the parameters, or you can easily develop the predictors for the future forecasts. You can also develop the tests for different hypotheses if you are using linear econometric models. Now, a specific aspect of linear econometric models is rate of change in y with respect to x j is constant and it is equal to beta j. For all the observations, this rate of change in y with respect to x j remains constant, and these models are appropriate when linearity appears to be a reasonable approximation, or even sometimes your model is non-linear, but by using a simple transformation, you can transform it into the form of a linear model. So, in these cases you can use the linear econometric models. So, for example, suppose we consider this non-linear regression problem, y equal to a e to the power b x into u. So, this u is actually a multiplicative error term. So, the model is non-linear, but if you take the log, then log of y is equal to log of a plus b x plus small u, where small u is equal to log of capital U. So, just by taking the logarithm, the model reduces into the form of a linear model. Again, we consider this Cobb-Douglas production function. So, y equal to a L to the power beta 1 k to the power beta 2 into u. Again, u is the multiplicative error term. Here capital Y is the total production, capital L is the labor input, capital K is the capital input, and then beta 1 and beta 2 are the parameters of the model. So, again your original model is non-linear, But if you take the log transformation, then log y is equal to log a plus beta 1 log L plus beta 2 log k plus small u is equal to log capital U. So, after taking this transformation, the model reduces into the form of a linear model. So, instead of applying the least square procedure to the original data, we take this kind of log transformation. We take log y, log L and log k, and then we use this model. We apply the least square procedure, and then you can estimate log a, beta 1 and beta 2. Now, we consider this example of constant elasticity of substitution, CES production function. Now, in CES production function, we take log qt equal to beta naught plus beta 1 log of beta 2 L2 to LT to the power beta 3 plus 1 minus beta 2 KT to the power beta 3 plus UT. Now, here you have the parameters in non-linear form. So, even we have taken log transformation, but you can't reduce the model in the form of a linear model. Here Q is the output, L is the labor input, K is the capital input. Again, in this model, actually we assume that beta 2 lies between 0 and 1 and beta 3 is less than 1, beta 1 is less than 0 or beta 1 greater than 0, it depends upon your conditions. So, now, in this case, transforming the model to linear form is not possible. You cannot transform this model into the linear form. So, you cannot apply the techniques of linear regression for fitting this model. So, in several cases, it may not be possible to transform the model in linear form. So, the alternative is to use some non-linear models, or you can use some non-parametric models also, or some semi-parametric models. Now, of course, in this lecture I am not going to consider these two models, non-parametric models or semi-parametric models. We will just consider the general theory of nonlinear models. Then nonlinear models pose a lot of challenges in terms of numerical implementation, how to estimate the model. It is a big challenge. Now, the analysis of the statistical properties of the nonlinear models is also difficult. So, you have two main issues: how to estimate the model, and then to investigate the properties of the estimators. Now, the general form of the model is, say, yi equal to h x I beta plus u I equal to 1 to n. So, yi is the observation on the dependent variable, then xi is a k cross 1 vector. This is observation vector on k explanatory variables. Then beta is the true parameter vector, and ui is the disturbance term. So, y is actually a function of xi and beta, this function h. So, obviously, if h xi beta is equal to xi transpose beta, then you get that linear model. Now, we make certain assumptions. The first assumption is about the functional form, say expectation of yi given xi is equal to h xi beta for all I. Then the second assumption is about the identifiability. There exists no non-zero beta naught, naught equal to beta such that h xi beta is equal to h xi beta naught for all xi. So, you cannot find two different values of beta having same value of h for all xi's. So, this beta completely identifies or specifies this function. For a single beta or for a specific beta, you get a specific value of h and you can't find two different values of betas leading to a single value of h. So, this is the condition of identifiability. Next assumption is disturbances have 0 mean. Just like the linear model, we assume that expectation of u I given h xi beta is equal to 0. So, this implies that the disturbance at observation I is uncorrelated with the mean function h xi beta. Expectation of u I given h xi beta is equal to 0. It does not depend upon h xi beta, or you can say u I and h xi beta are uncorrelated. Next assumption is homoscedasticity and no autocorrelation for disturbances. Just like the linear regression model, we assume that expectation of u I square given h xi beta is equal to sigma square u for all I equal to 1 to n. So, this is the assumption of homoscedasticity. And then expectation of u I u j given h xi beta h xj beta is equal to 0 for all I not equal to j. So, for different I and j, u I and u j are uncorrelated given h xi beta h xj beta. Then the fifth assumption is about the data generating process. The data generating process for xi's is well behaved and the first two moments of xi's converge to fixed finite population moments. Again, we make this kind of assumption for the linear regression model also. So, we assume that the first two moments of x's converge to finite and fixed population moments. Then underlying probability distribution disturbances ui's are IID with mean and variances conditional on h xi beta equal to 0 and sigma square u. This assumption we have already taken. Sometimes we require the assumption that ui's are normally distributed. So, sometimes we also assume that ui's follow normal distribution. And then if disturbances are normally distributed, then actually f y I given xi beta sigma square u is equal to 1 upon under root 2 pi exponential minus 1 upon twice sigma square u y I minus h xi beta square. And if you take log of this, then you obtain minus half log of 2 pi here. So, you get minus half, you take minus half common log 2 pi and then you have minus 1 upon 2 sigma square u, you have sigma square u here also. So, and then you have y I minus h xi beta square. So, again we take minus 1 upon 2 common. So, you get minus 1 upon sigma square u y I minus h x I beta square, and then you have sigma square u here also. So, you get minus log sigma square u, and you are taking minus half common. So, log of f y I given x I beta sigma square u is equal to this. Then, if we take del over del beta log f y I given x I beta sigma square u, then we obtain, we differentiate it with respect to beta. So, differential coefficient of this part is 0. Here you obtain, you have minus half here, then minus 1 upon sigma square u. So, you get plus 1 upon 2 sigma square u, then you are going to differentiate this part. So, you get 2 here y I minus h x I beta, and then again you get minus sign from here, and we differentiate h x I beta with respect to beta, and then y I minus h x I beta we write equal to u I. So, we get del over del beta log f y I given x I beta sigma square u equal to 1 upon sigma square u del h x I beta by del beta into u I. Actually, you have written y I minus h x I beta equal to u I, and then we take expectation of this and we write it equal to 0. So, derivative of h x I beta and u I are uncorrelated. Then, for the linear model we require the condition expectation of x I into u I equal to 0, and using this condition we can get the least square estimator. Actually, for obtaining the least square estimator as generalized method of moment estimator, we require this kind of condition. X i's and u i's are uncorrelated. For nonlinear model, we require this condition to produce least squares as GMM estimator. So, a proper definition of nonlinear regression model is a model is a nonlinear regression model if the first order conditions to obtain OLS estimators are nonlinear functions of parameters. So, here if the condition is nonlinear, then your model is nonlinear regression model. Now, you have this nonlinear regression model y equal to h x beta plus u. Then, using the Taylor series approximation, we write this model in linearized form. So, we use Taylor series approximation at beta naught, say. So, at beta naught, beta equal to beta naught, we have the Taylor series approximation h x beta approximately equal to h x beta naught plus summation j equal to 1 to k del over del beta j naught h x beta naught beta j minus beta naught j. And then we ignore the higher order terms involving beta j minus beta naught j square or cross products, etc. So, this form is called the form 5 is called the linearized regression model. Then we can write this model as say h x beta equal to or approximately equal to h x beta naught, and then you have a term here minus summation O j del O del beta j naught h x beta naught beta j naught. So, we have collected the terms not involving beta j, and then we have the term summation O j del O del beta j naught h x beta naught into beta j. So, we get this form 6. Or you can approximate h x beta as h naught minus x naught transpose beta naught plus x naught transpose beta. So, in fact, we have taken x naught transpose equal to summation del O del beta 1 naught h x beta naught, then summation del O del beta 2 naught h x beta naught, and so on, summation del O del beta k naught h x beta naught. So, this is the vector x naught transpose, and then x naught transpose beta naught is equal to summation j equal to 1 to k del O del beta j naught h x beta naught into beta j naught. Similarly, x naught transpose beta is equal to, you can write x naught transpose beta also, which is equal to summation O j del O del beta j naught h x beta naught into beta j. So, using these notations we can write h x beta approximately equal to h naught minus x naught transpose beta naught plus x naught transpose beta, and then you can write y as y approximately equal to h naught minus x naught transpose beta naught plus x naught transpose beta plus u. Now, this is somewhat like the linear regression model. This is your intercept term, and then you have this term also. Now, you write y naught equal to y minus h naught plus x naught transpose beta naught. Then 7 becomes y naught equal to x naught transpose beta plus u naught. In equation 7, we have taken h naught and minus x naught transpose beta naught towards the left hand side. So, you get y minus h naught plus x naught transpose beta naught equal to x naught transpose beta plus u, and then we are writing y naught equal to y minus h naught plus x naught transpose beta naught. So, you get this model 8. Now, this u naught actually contains both the disturbance term u and error of first order Taylor series approximation. So, your original model has this disturbance term u, then you have approximated this function by using the Taylor series expansion, and then actually you have taken just the leading term. So, naturally there is some error of first order Taylor series approximation. So, this u naught includes both u as well as the error of first order Taylor series approximation. So, for given beta naught we can compute y naught, So, for the fixed beta naught you can obtain this. You can also compute x naught, and then you can estimate beta by using the least square procedure to equation 8. So, you can directly apply OLS procedure to this equation, provided you have some initial value beta naught. Beta naught is known. For example, if we consider this model y I equal to beta 1 plus beta 2 e to the power beta 3 x I plus u I, then for given beta naught, as beta naught is equal to summation I y I minus beta 1 naught minus beta 2 naught e to the power beta 3 naught x I whole square. And then if we differentiate this s with respect to beta 1 naught, we obtain minus twice summation y I minus beta 1 naught minus beta 2 naught e to the power beta 3 naught x I equal to 0. You have this term. And if we differentiate s beta naught with respect to beta 2 naught, then we obtain del over del beta 2 naught s beta naught equal to minus 2 times summation y I minus beta 1 naught minus beta 2 naught e to the power beta 3 naught x I into e to the power beta 3 naught x I. You have this term also equal to 0. So, you get these two equations. Similarly, if we differentiate with respect to beta 3 naught, then we get del over del beta 3 naught s beta naught equal to minus 2 times summation y I minus beta 1 naught minus beta 2 naught e to the power beta 3 naught x I into, now we differentiate this term with respect to beta 3 naught. So, we get beta 2 naught into, you differentiate this part. So, you get x I and then e to the power beta 3 naught x I if you get here, and then we write it equal to 0. So, the equations in the linearized equation are, say we have x 1 naught equal to del over del beta 1 naught h, and then this is equal to 1. What is h? H is equal to beta 1 plus beta 2 e to the power beta 3 x. This is your h x beta. Then x 1 naught is equal to 1. X 2 naught, which is equal to del h over del beta 2 naught, this is equal to e to the power beta 3 naught x. You can easily verify it. If you differentiate with respect to beta 2, you get this term, and then we write beta 3 equal to beta 3 naught. And then x 3 naught is equal to, we differentiate with respect to beta 3 naught. So, you obtain, you write beta 2 equal to beta 2 naught. So, you get beta 2 naught here, and then you have x e to the power beta 3 naught x. So, you get these values of x 1 naught, x 2 naught and x 3 naught for this example. So, for given beta naught, you have y naught equal to y minus h x beta 1 naught, beta 2 naught, beta 3 naught plus beta 1 naught x 1 naught plus beta 2 naught x 2 naught plus beta 3 naught x 3 naught. you have already defined x 1 naught, x 2 naught and x 3 naught. And then we can estimate beta equal to beta 1, beta 2, beta 3 transpose by regressing y naught on x naught equal to x 1 naught, x 2 naught, x 3 naught, x 3 naught. So, once you transform the model using Taylor series approximation into this linear form, then what you have to do, you simply obtain y naught and then x naught, this vector which is equal to x 1 naught, x 2 naught, x 3 naught, and then you obtain the OLS estimator for beta. Of course, we assume that we have known initial values beta 1 naught, beta 2 naught and beta 3 naught. Now, for large sample properties of this estimator, we assume that the probability limit of 1 upon n x naught transpose x naught, which is equal to probability limit of 1 upon n summation del over del beta naught h x I beta naught del over del beta naught transpose h x I beta naught is equal to q naught, and then this q naught is a positive definite finite matrix. So, just like the linear regression model, here instead of x we are taking x naught, and then we are assuming that the probability limit of 1 upon n x naught transpose x naught is a positive definite finite matrix q naught. The second condition is orthogonality condition. Here we assume that 1 upon under root n summation x I naught u I is equal to 0. In linear regression model, we assume that 1 upon under root n summation x I u I is equal to 0. Here the orthogonality condition is that 1 upon under root n summation x I naught u I is equal to 0. Then for asymptotic normality, we require the condition 1 upon under root n summation x I naught u I tends to the normal distribution with mean 0 and variance covariance matrix sigma square u q naught. So, this is the assumption for asymptotic normality. Then non-linear least squares estimator is obtained by minimizing S b equal to, we just take half here summation I equal to 1 to n y I minus h x I b whole square. So, this is the other sum of squares, and just for convenience we have taken half here, although it does not matter whether you take half here or not, and then this is equal to 1 upon 2 summation u I square. Then for obtaining the first order condition, we differentiate it with respect to b. So, you get summation I equal to 1 to n, you get 2 here. So, 2 will cancel out. So, you get y I minus h x I b del over del b h x I b equal to 0. Again, I am not going to give you the proof of this result. Say under the conditions, say beta belongs to a compact parameter space, and for given beta naught, the probability limit of 1 upon n s beta naught is equal to q beta naught, and this is continuous and differentiable. Then q beta naught has a unique minimum at true beta. So, actually what you are doing, you are minimizing this. So, and then we write the probability limit of 1 upon n s beta naught equal to q beta naught. Then under these conditions, this q beta naught has a unique minimum at true beta, at beta naught equal to beta. Then under these conditions, the least squares estimator produced by 9 and 10 is a consistent estimator of beta. So, if we take these conditions, then this leads to a consistent estimator of beta. Again, I am not going into the details of the proof here. And the asymptotic distribution of B is normal, having mean vector beta and variance covariance matrix sigma square u upon n q naught inverse. So, from here also you observe that the asymptotic distribution of B has mean beta, and as n tends to infinity, its variance covariance matrix tends to 0. So, this shows that B is a consistent estimator of beta. Again, the an estimate of asymptotic variance covariance matrix of B is sigma hat square u x naught B transpose x naught B whole inverse. So, we calculate x naught B at B, then we obtain x naught B transpose x naught B, and then an estimate of variance covariance matrix or asymptotic variance covariance matrix of B is sigma hat square u x naught B transpose x naught B inverse, and sigma hat square u is obtained as 1 upon n summation y I minus h x I B whole square. Now, in practice, the algorithm for computing non-linear least square estimator is, say we start with a given value of beta naught. So, this is the initial value of beta naught, and then for given beta naught we estimate beta using linearized regression model using the procedure which we have described earlier, and say we get the estimate beta 1. Now, we replace this initial value of beta, say beta naught, by beta 1. Again we compute the linearized regression estimator. So, again we repeat the procedure, we obtain x naught, y naught, etcetera, and then we estimate beta, and suppose you get the estimator beta 2. Then we continue these iterations. So, we replace beta 1 by beta 2, again we obtain the estimator by using the linearized regression model, and so on. So, we continue iterations until the estimators converge, that is, the difference between estimators of successive iterations is small enough, and once the estimators converge, then we stop, and then we get the OLS estimator. So, here at the t plus 1th iteration, you have B t plus 1 equal to summation I equal to 1 to n x I naught transpose whole inverse, and this is the estimator obtained in the previous iteration at the tth iteration. So, you have summation I equal to 1 to n x I naught y I minus h I naught plus x I naught transpose B t. So, this is actually the value of y I naught at the previous iteration. This is based on B t, and then you can write it as, say you combine this term with this. So, you get summation I equal to 1 to n x I naught transpose inverse, and then you have summation I equal to 1 to n x I naught transpose B t. So, ultimately you get P t here plus summation I equal to 1 to n x I naught transpose inverse, summation I equal to 1 to n x I naught y I minus h I naught. Now, y I minus h I naught is the error or estimate of error at the tth iteration. So, B t plus 1 is equal to B t plus, and then we write summation I equal to 1 to n x I naught transpose in matrix notation as x naught transpose x naught whole inverse, and then this term is equal to x naught transpose E naught t. E naught t is equal to y 1 minus h 1 naught, y 2 minus h 2 naught, y n minus h n naught, or this is equal to B t plus you write it equal to delta t. So, E naught t is the least squares residual at the tth iteration. Then all the terms on the right hand side are calculated at B t. So, whether you are calculating x I naught or the y I naught, you are calculating all the terms at B t. So, you can use this iterative procedure for obtaining or for updating B t. Then the convergence criterion is, say, delta equal to capital delta t transpose delta t, and then delta t is equal to this term. So, you get E naught t transpose x naught, then in between you have x naught transpose x naught inverse x naught transpose E naught t. So, this is your convergence criterion. So, at each iteration we calculate this quantity, and then if the initial value is far from the true value, then you face one problem. It may happen that this algorithm jumps off the true estimate. So, even after the large number of iterations, it does not converge. So, selection of initial value is also very important, because if you are selecting the initial value far from the true value, then you face this problem of jumps off, and in that case the algorithm or these iterations may not converge. So, if you face this kind of problem, then you must try some other initial value. Then the coefficient of determination r square is defined as r square is equal to 1 minus summation I equal to 1 to n E I square upon summation y I minus y bar square. So, this is how you can define the r square for nonlinear model. Then testing for parameter restrictions. So, suppose you want to test the hypothesis H naught r beta equal to small r, where this r beta is a q cross 1 vector of continuous functions of beta. So, actually different elements of r beta, these are functions, continuous functions of beta. Then the restrictions may be linear or nonlinear. So, this may be a nonlinear function of beta. Say, for example, in CES production function, you have the model log q t equal to beta naught plus beta 1 log beta 2 L 1 to the power beta 3 plus 1 minus beta 2 k t to the power beta 3 plus u t. And we are often interested in the hypothesis of this form. So, beta 1 into beta 3 equal to 1, which is equivalent to the hypothesis that beta 1 minus 1 upon beta 3 equal to 0, because beta 1 is equal to 1 upon beta 3 or beta 1 minus 1 upon beta 3 equal to 0. So, you have this hypothesis. So, here this r beta is not a linear function of beta 1 and beta 3, it is a non-linear function. Then we assume that r beta minus small r impose at least one relationship. So, at least one restriction you must have. Then the relationships are linearly independent. So, all these relationships must be linearly independent. So, then Q cross K matrix del over del beta transpose R B must be full row rank. What is the order of this matrix? This is of order Q cross K. R B is of order Q cross 1, then beta is of order K cross 1. So, if you consider this del over del beta transpose R beta, then this is of order Q cross K. And then this automatically implies that the number of restrictions Q is less than K. Now, suppose B is the non-linear least squares estimator without imposing the restrictions, and B star is the restricted non-linear least square estimator. So, along with your model, which is also a non-linear regression model, you also consider these restrictions, and we combine the non-linear restrictions and non-linear regression model, and then we obtain the restricted non-linear least square estimator, say B star. And then S B is the sum of squares of residuals under unrestricted case, and S B star is the sum of squares of residuals under the restricted estimators case. Then F statistic is defined as F q n minus k equal to S B star minus S B divided by the degree of freedom q, a number of restrictions q, and then we divide it by S B upon n minus k. And under the null hypothesis of restrictions r beta equal to small r, this follows F distribution with q n minus k degrees of freedoms. Now, you can easily form the critical region for testing the hypothesis. If this calculated value is greater than the tabulated value, then we reject H naught, otherwise we accept H naught. Then wall test. So, it is based on the distance between R B and small r. So, we take R B minus small r transpose, then in between we have estimate of asymptotic variance covariance matrix of R B minus small r whole inverse, then R B minus small r. And then this is equal to R B minus small r transpose, and then we substitute the value of estimated asymptotic variance covariance matrix of R B minus small r here, which is R B, we had R B transpose whole inverse, then R B minus small r. V hat is the asymptotic values covariance matrix of V, the unrestricted least square estimator, and under H naught the statistic follows a chi-square distribution with q degrees of freedoms. The next test is Lagrange's multiplier test. So, suppose E star is the vector of the residuals under restricted regression with ith element y I minus h x I b star, and then x naught is n cross k matrix of derivatives computed at a particular beta naught. Just like what we have defined earlier, we define x naught at beta naught. Then x naught star is the matrix of computed at restricted estimates. So, this matrix is obtained or this matrix is computed using the restricted estimates. Then LM test statistic is, say, E star transpose x naught star x naught star transpose x naught star inverse x naught star transpose E star divided by E star transpose E star upon n, and then under H naught this statistic has a limiting distribution chi square q. Again you can easily form the critical region. If this calculated value is greater than the tabulated value of chi square at say alpha level of significance, then we reject H naught, otherwise we accept H naught. We can also form the confidence intervals, say from the asymptotic normality of B, the 101 minus alpha % confidence interval for beta I is given by, say, B I minus Z alpha by 2 sigma hat u under root C I B I plus Z alpha by 2 sigma hat u under root C I, where this C superscript I is the ith diagonal element of x naught B transpose x naught B inverse. So, what you have to do, you have to calculate this, and then C superscript I is the ith diagonal element of this, and then you can easily obtain this confidence interval. Here Z alpha by 2 is the 1 minus alpha by 2th percentile of the standard normal distribution. Now, we can also obtain the joint confidence interval for the coefficients vector beta by using the 3F statistic which we have defined earlier. Say F1 beta, which we have defined as S beta minus S b divided by k upon S b upon n minus k. So, if we use this statistic, then using this statistic we can form a joint confidence interval for beta. Then F2 beta is beta minus B transpose, then in between we take del 2 S over del beta transpose at beta equal to B. Then beta minus B divided by 2 k upon S b upon n minus k. And the third F ratio is F3 beta equal to beta minus B transpose x naught B transpose x naught B beta minus B divided by k upon S b upon n minus k. So, you can use these statistic for defining a joint confidence interval for beta. Again, I am not going into the details of derivation of these F ratios or F distributions. So, asymptotic distribution of all the three statistic is F, k and minus k. And then we can use these test statistic or these statistic for forming the joint confidence sets. So, we form the confidence set as the set of values of beta such that f I beta is less than or equal to f alpha k n minus k. This is the tabulated value of f distribution at k and n minus k degrees of freedoms and alpha level of significance. So, this is how you can form the joint confidence set for beta. So, the linear regression models are quite popular and widely used in many applications because of simplicity in estimating the parameters or obtaining the predictions, etc. But in many applications, these models do not provide reasonable approximations, and in many applications the nonlinear models which we get cannot be transformed to linear models by using a simple transformation. So, in those cases you require nonlinear regression models. So, in this lecture we have discussed different estimation procedures, the algorithms for estimating the nonlinear regression models. We have also discussed the testing of set of restrictions, nonlinear restrictions for the parameters of the model, and the confidence interval estimation for an individual coefficient as well as a set of confidence interval or a confidence set for the regression parameters vector beta. So, I am going to stop here. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.